Hello, my name is Gary Pocock and this is my week 4 reflection for the Physics Modelling Instruction course. Alright, this week I want to talk about 3 different things. The first 2 arise from last week's online session. It's the field concept discussion that we had last week, and also a discussion on field lines versus field vectors. And finally, I want to talk about the experiment that we had to complete at home, which was determining the charge on a tape. Alright, field concept first of all. Alright, this was a very interesting discussion that was had last week, and I think it was raised by Craig. And he just put out the provocative question, why do we need to have field lines anyway? Why can't we just be satisfied with the force concept for explaining everything? And people put forward a number of suggestions, and many of which are really good and which I've used myself in the past. And the most obvious one was we use the field concept, or scientists develop the field concept to get around the fact that the force seemed to be acting over a distance with no medium between the two objects. And the field concept was hypothesized as an explanation for what is mediating between the two objects when there is an electrical force between them. I was reflecting on that afterwards, and reflecting on just why it is so difficult for students to grasp the field concept, and why, even though we give them the mediating the force explanation, it somehow rather feels not entirely satisfying to the students. And there are a couple of extra things that I thought of after the session that I could possibly add to that discussion. The first was historical, and it's just going back to Galileo and Newton, and also going back to concepts of what is a scientific law and what is a scientific theory. And what the historians of science tell us is that one of the key things that Galileo did was not ask a why question. So when he was actually trying to understand how objects fell according to gravitation, he focused on the what is happening, not the why. He tried to describe what was happening and actually set aside the task of explanation. And his reasoning was that you need to understand exactly what is going on before you attempt to explain why. And of course this made no sense to those immersed in the Aristotelian approach, because everything you did in their approach to things was all about explanation. So simply saying that an object fell at a certain rate of acceleration was nothing at all to the Aristotelians without an explanation for why that was happening. But Galileo managed to make progress by not attempting to address the why question. And then when we come to Newton and the law of gravitation, Newton famously proposed his law of gravitation, but then famously said, I make no hypotheses. He didn't attempt to explain why. I mean, he would have liked to, obviously, but he wasn't able to provide an explanation at that stage. So once again, he made progress by hypothesizing a description of how gravity behaved in terms of his law of gravitation without providing an explanation of why. And so we can see in general that that is what force laws are doing. When we come to proposing a field, we are actually moving beyond the law, and we are trying to provide a theory for why the force is acting in the way it is. And that's what fields are doing. They're trying to fill that gap. And furthermore, they're trying to address the concern of the scientists that it just doesn't seem scientifically plausible that you could have a force acting over a distance without some kind of intermediate medium acting between them. So that's my first thought. The second one, I think one participant, I think it might have been Leif, he posted a link to a Feynman video in which Feynman is asked, how do you explain the magnetic force? And Feynman launched into a brilliant explanation of what it is to explain something and why it is so difficult to explain what a magnetic force, or in our case, what a field, or in our case, what a electric field is. And his conclusion was, in order to explain something, you need to explain it in terms of something else that is familiar to you, that is taken for granted, that is understood by you. And his response to the questioner was, I can't explain magnetic force, or in our case fields, in terms of anything else that is familiar to you. Fields are a more fundamental concept, and I think that's essentially why we have such difficulty, or students experience such difficulty in accepting fields, because they're looking for an explanation in terms of something that is familiar to them, and that is fundamentally not possible, because we are using fields to explain things that we think that are familiar to us. So fields are the more fundamental concept. Again, that's a very difficult concept. Students will struggle with that one, but I really think that's one worth putting out there. And that Feynman video, it's only 7 minutes, and he gives a brilliant explanation. Okay, moving on. Something else that came up during the last week's session was the field lines representation versus the field vectors representation, and someone made the comment that that seemed to have been skipped over fairly quickly in the worksheet that we were working on. I thought that was a good point, and on reflection, I felt that's probably something I skip over a little bit too quickly with my students, and it's something where I probably should be developing some questions where I really draw out the similarities and differences between the two, and the advantages and disadvantages of each one. Why field lines give us a nice visual overall picture of the shape of the field, but at the same time it doesn't give us an entirely accurate representation of the magnitude of the field at various points. It gives us using density of field lines, we get a rough idea of the strength of the field, but the field vectors give us a better picture of the strength of the field at various points. So just developing some questions where those two methods of representation are put side by side and clarifying the strengths of the two, I think would be very helpful. Alright, that's all I had to say about that one. So now moving on to the charge on tape lab that we did. Alright, first point I have to say is I think this is a fantastic lab for students to do as a summing up of the whole electrostatic unit. It's quite remarkable that with such simple equipment you can actually get any kind of quantitative estimation for the number of electrons on a charged tape, or the number of excess or deficit of electrons on a charged tape. It's also a great experiment in another way, in that well, first of all, you have to really think quite hard about how you're going to set it up. The way I set it up was just using 2 vertical tapes, and I attached them to retort stands. I could see how you might want to do this using horizontal tapes, because one's first reaction when using vertical tapes, which then repel at an angle, is you've got this tension force, and and you don't know anything about it, so what the heck can you do with that? So I was tempted initially to go with a horizontal version of it, hovering one tape horizontally above the other and getting it to repel, but that seemed to me to be somewhat awkward and possibly needed more than one set of hands to do. And I realized how I could do mathematically the version with the vertical tapes, and so that's the way I went. But then once you do that, some surprising complications can turn up, and so as a student this would be really good, because you have to think hard about how to improvise and deal with the tricky details of tapes sticking to your hands. And in my case, I'd set my tapes up on a retort stand, and the first thing I discovered is when you attach a 30 centimeter tape to a protruding rod on a retort stand, it attracts to the metal in the rod, in the stand. So I had to improvise and come up with ways of getting the tape further away from the actual stand itself, so I could minimize the attraction between the tape and the stand. And just other practical details about how there's a real technique for stripping the tape off the base tape to make it charged in such a way that it doesn't stick to your arm in the process. So there were lots and lots of little details, and this is something that would be very valuable for students to work through. The other comment I had on this experiment was one of the questions was do the mathematics and write down the equations and determine an equation for the electrical force, which I did in the assignment. But it struck me that when I'm working with my students, what I would really like to do is get them to do the scale diagram, even if they can do trig, because I think that it's a really nice visual representation of how you can take a situation when you've got two unknown forces, the tension force and the electrical force, and just by knowing the fact that the electrical force is horizontal and also knowing the angle at which the tape is deflecting, you can actually determine both of those unknown forces. And the final thing that I was going to say about that experiment was version of the experiment. You come up with that the electrical force is equal to the gravitational force times tan of the angle of deflection. Now in my case the angle was 22 degrees, which as a decimal comes out, well, tan 22 comes out as 0.4. So the formula is saying that the electrical force is 40% of the gravitational force between the tapes. And that's, I think, a really nice point for students to reflect on. That just by creating a static charge on two tapes, you can create an electrical force whose strength is 40% of the gravitational force between this tape and a massive object such as the Earth. So that, I think, is a really nice way of bringing out just how strong the electrical force is in comparison to the gravitational force. To the issue of the practical details of the experiment and how you have to, there are lots of little surprises that you have to address along the way. My first surprise was that you really do have to use Scotch tape for this experiment. Initially I started using a different brand of tape, and the experiment simply didn't work. This tape simply would not pick up sufficient charge to get repulsion. As soon as I got out some Scotch tape, it worked just fine. And the second little discovery that I made while I was doing it was I used linear mass density. So I was taking sample bits of tape and measuring their mass and length, and I did it a few times because I was surprised that you actually get quite a little bit of variation between them. And in particular, if you've got a piece of tape that's near